So this is example 1.26 on electrical quantities, and it's a case study question. The question says that in dry powder coating, charged dry paint particles are guided towards the target surface by an electric field between the powder spray nozzle and the target. The voltage difference between the nozzle and the target is 1 kilovolt, and the distance between the nozzle and the target surface is 10 centimeters. Estimate the force on a paint particle carrying a charge of 2 picocoulombs. If the powder flow rate is 10 to the 6 particles per second, calculate the electric current and power supplied to the nozzle to charge the paint particles. So where do we start with this? Well, let's start. The first part of the question asks us for the force, and then we're asked after that for electrical current and power supplied to the nozzle to charge the paint particles. So let's start with force. Okay, let's find an equation with force in it. And as a demonstration, this is the diagram to show what's actually going on. So we've got this spray nozzle and we've got this target. We're spraying powdered paint particles onto it. Okay, so they're dry powdered paint particles that have a charge. In between the target and the spray nozzle, we have an electric field, and distance between the spray nozzle and the target is 10 centimeters. So from the spray nozzle, you get these powdered things going in all directions. Okay, now the power supplied to the spray nozzle is 1 kilovolt. That doesn't refer to the voltage between these two. Sorry, that does refer to the voltage between these two. And notice here that the target is earthed, meaning that it's safe. Meaning that it goes back towards Earth and the connection goes back. Okay, so it forms a circuit. So we have this electric field E here, and we know the force acting on the particles. Okay, so let's start. Well, we previously said that V, our voltage, is equal to the integral from 2 to 1 of F dl. This expression here, F dl, is work done over our Q. So our definition of voltage is force, or work done, sorry, per coulomb, per unit charge of coulomb. But we can simplify this down by replacing F over the Q with E. So eventually what we get is 2 to 1 E equals, sorry, multiplied by dl. Okay, E is electric field. Okay, so E is the same as F over Q. Okay, so its units are newtons per coulomb. This is our electric field. Okay, so this is our electric field strength. So we've got this expression here. Now, what we have to do in these problems is that we have to assume that this electric field here is uniform, and that the electric force is also uniform, which is obviously a big assumption, but it's useful. And for these simpler problems, we'll have to do this until we learn more techniques. So assuming that the electric field is constant, we can reduce this equation to V is equal to F L over Q. Notice the dl is gone because we're no longer talking about infinitesimal quantities, we're talking about a certain distance L. Okay, again we can rewrite this as EL. Okay, so electric field times L. Now from this we can calculate the force on a powdered particle. Okay, because we've got F in this expression. So in fact we didn't actually need to show this, but this was just to highlight, because we're just learning the course, highlight that this E value does exist. Okay, so let's rearrange this part of the equation here to make F the subject. Well, what do we get? We get F is equal to QV, the charge, times the voltage, over L, our distance between the spray nozzle and the target. Okay, so this is what we use to calculate the force, okay, on each powder particle. So we just simply substitute numerical values, and we say that we know that Q is, each one carries this much charge, the voltage between them is this much, and the distance between them this much. Simple maths, and what we find is that F is equal to 2 times 10 to the minus 8 newtons. Okay, so this is a force. So each particle going between the spray nozzle and to the target, as it goes through this electric field, okay, because of the charge it carries, has that much force on it. Okay, now this is obviously a proportional relationship, so if we increase the distance, the force would decrease. Okay, so this is how much force is on each particle. Okay, so force on each particle. okay, or each paint particle. That's how much force we have on each paint particle. Okay, so that's fair enough. Okay, so let's just make some space. Next part of the question asks us something different though. Next part of the question asks us for electric current and calculate the electric current and power. Okay, so we'll come to that in a second. So we work out this is our force. Okay, so this is the force on each particle. Now what about electric current? Well, we've got expressions for electric current and we've got expressions for power as well. So let's put them to use. Now, before I go on to finding the current and the electric current and the power, let's just talk about this value here. We know it's obviously a very small force, but the particles are also small, so you've got to put this into consideration. Typically, each particle would be between 50 to 100 micrometers in diameter. And of course, there's also a gravitational field acting on these powders, okay, and obviously drag forces, etc., etc. And we have to think about how do these forces compare to the electric force. Are they stronger? Are they weaker? Of course, in this case, we can see they're stronger, otherwise the paint particles wouldn't reach their target. Now, the exact path taken by the powder particles will depend on all these forces in addition to the force of interaction between the charged particles. In fact, the electric field lines wrap around the target and the target is coated all over. The electrostatic powder coating process is self-limiting. What does this mean? Well, it means simply that the powder layer does not continue to grow indefinitely as the charged particles that adhere to their target first repel charged particles arriving later. So it's a pretty nice process, because what happens essentially is as certain spray powder particles embed themselves onto this surface, they repel further on, so you get a nice clean finish. Now we move on to the next part of the question. Now what we do for the next part of the question, again we've got to make an assumption, and our assumption in this bit is assume that the total number of particles sprayed at any moment in time is n. So we're given an arbitrary number n, so that therefore the total charge will be Q is equal to, so our total charge will be equal to Qn. Okay? The rate of particles sprayed every second will be dn dt, okay, which seems to make sense. N is our number of particles, t is respective time, so this, and we're given this as 10 to the 6 per second. This is 10 to the 6 particles per second, okay? In fact, if we're going to, okay, so it's just 10 to the 6 per second. So we have this many particles spraying, going past a particular point per second, okay? So we use equation 1.5 in the notes to find current. So we know that I, current, we use a small I in this case, is equal to dq dt. Okay, remember, current we defined as the rate of flow of charge. Q is charge here. But we know Q is equal to this, so we say d of, substitute the same, nq over dt. Okay, what does this give us? Well, Q here is constant, okay, but this is Q dn dt. Okay, well, what does this equal? Well, this is 2 times 10 to the minus 12 times dn dt. Okay, so we've got Q, because that's pico is times 10 to the minus 12, and dn dt is 10 to the 6. Okay, so times 10 to the 6. Okay, what do we get? Well, we get 2 times 10 to the minus 6, which seems to make sense. Okay, amps. Amps are the SI unit for current. Now this is a pretty large number, so we want to express it in simpler form, so we just say 2 microamps. Micro refers to 10 to the minus 6. Okay, so we've got our current. How do we find out power? Well, power in terms of electricity is equal to VI, so V times I. Well, V is our voltage, we know that, and I is our current, because we just worked it out, which is simple. It's 1,000. Remember, it's 1 kilovolt is 1,000 volts, and express it always in terms of volts in SI unit, times our current, which is 2 times 10 to the minus 6. This gives us 2 milliwatts, sorry. Okay, it's 2 milliwatts because this would be 10 to the minus 3, because this is 10 to the 3, this is 10 times 10 to the minus 6, so it's reduced to 10 to the minus 3. So that gives us 2 milliwatts. Okay, so we've worked out our power, and we've worked out our current, and we've worked out the force on each particle. These three were our values. Okay, these are our answers. That's the end for this question. Thank you.